Okay, so on this page, okay, if you want to watch that video again, come to the OneNote. I've got it linked in there. He's pretty famous in the world of physics and YouTube. Like he's an MIT professor, or he was an MIT professor. And a lot of his lectures are online. I think we've seen at least one other demo that he's done. But here we have rolling objects released from rest. And so they're different. We got some solid sphere, hollow sphere, solid sphere of a different mass, and then a hoop. And so the question is, they give you the shape constants, rank the 4 objects from fastest, in other words, the shortest time, who wins, down the ramp to the slowest, who loses. And so which one always loses? Hollow, but here we have a hollow sphere and a hollow hoop. So who's going to be the loser? Why the hoop? It has a higher K. So the constant for hoop is an understood 1 there. The hollow sphere, they tell us, is 2/3. And so the bigger the K, the bigger the inertia, the harder it is to rotate down the ramp. Okay. And we could do a net torque statement, which we'll probably end up doing that on this problem next time. And so the hollow hoop is going to be the loser. Hollow always loses. Okay. And then we've got the hollow sphere. B would be the next loser. Who's going to be the winner? We've got a solid sphere at 1 kilogram and a solid sphere at 2 kilograms. Does mass matter? No. And so A equals C, greater than B, greater than D. Hollow always loses. Okay. And in case you don't remember, I don't say always often, right? But hollow always loses. Yes. Say what? Calculate the mass with the inertia? So I haven't written it out yet, but here in next class, we're going to do a conservation of energy statement. Potential at the top, MGH, equals 1/2 mv squared as it goes down the ramp, right? Kinetic energy. And you're in your non-slip situation, your 1/2 I omega squared reduces to 1/2 K mv squared. Mass cancels. Mass is going to cancel, you'll see. Okay. And so that's where we'll pick up next time. Hollow always loses.